All right, ladies and gentlemen, class recording has started, hopefully better than yesterday. So, over the past couple days, we've been talking about this idea of energy, and then yesterday we introduced the idea of work. And work we defined as a transfer of the energy between objects. And that means that when work is done, energy changes. That's what work does. It changes the energy of two objects. One object is going to increase in energy, one object is going to decrease in energy. And yesterday, we went through this discussion here about where our definition of work comes from, and we came to the realization that in order for work to be done, in order for the energy of an object to change, two things have to happen. There has to be force applied to that object, and the object needs to move because of it. And we went through all the situations yesterday and talked about is it work, is it not work, etc., etc., etc. Okay? But how much work is done and how much does that change the energy? Well, going back to this derivation, starting with a Suvat equation, right? Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement, we ended up eventually down here, right? With the change in kinetic energy being equal to force times displacement, right? And I showed you in the original video how we got that, how we manipulated the equation, etc., etc. As far as looking at the quantitative relationship between work and energy, we end up here with the work-energy theorem. The amount of work done on an object is equal to this corresponding change in the energy. Now, this is kinetic energy here in the equation, but we'll find out tomorrow that we can turn kinetic energy into other forms of mechanical energy. So what we realize, or what we come to the conclusion, is that whenever work is done, there's a change in energy. And however much work is done, that's how much the energy changes. All right? Good there? So, yesterday we sort of introduced this concept as we go along, but depending on how the force is oriented with the motion of the object, that can change the energy in some different ways. So we can have positive work where the energy of an object increases, or we can have negative work where the energy of an object decreases. And we can see here, or we can give this kind of picture right here, right, that depending on how we apply the force in relation to the motion, that can cause the energy to increase or decrease. Right? So if we help the motion, if somehow we either push or pull an object in the direction that it's already going, or if it's at rest and it moves in the direction we're pushing, that will increase the energy. It will make it go faster, or it will make it go higher if we talk about pulling it straight upward. All of those things cause an increase in energy, either kinetic or potential. But if we somehow pull against or push in the opposite direction that an object is moving, that's going to decrease the energy. All right? Good there? So, on the sheet that I gave you yesterday that talks about all the applications of work, you have this example down at the bottom. And it says, each of the can you guys see? Do we need to put a little bit of light on, or are we getting ready okay? Okay. So, what? So, I mean, we could put just one light on, so you can see it's a little bit.
It strains my eyes.
It strains your eyes more than looking at this bright white board in a dark room. It's like a movie theater. If we had some surround sound, this would be like. All right. So here it says each of the boxes shown below moves through the same horizontal distance d, and those horizontal distances are shown here in this picture. Right? It says the force applied to each of the boxes has the same magnitude F. So the force applied is the same amount of force, but as you can see, right, the direction of the force is different in each of the cases A, B, C, and D. So it says rank these cases in order of increasing work done by the force from most negative to most positive. All right? So what's going to be the most negative force? B, right? B is going to be negative work because the box is moving to the right, but the force is being applied to the left. So if we're ranking these from most negative to most positive, this would be number 1. Okay? Negative work. It's going to cause that box to slow down. All right. What's going to be next? A. How much work is done on box A? What? How much work is done by this force in box 1, or in case A, I'm sorry. No work is done by that force, right? Because this, I should have done this. This is negative work, right? The next amount of work done here is 0. Remember, only forces that act in the dimension of motion will do work. This force does no work on that box. Now, if you had a box sliding across the floor and you pushed down on it, what would happen to that box? It would stop. But it's not this force that's actually causing it to stop. What is causing it to stop? Friction. By pushing downward on it, what are you actually doing? You are not increasing the weight. You're increasing the normal force, which we saw in the last chapter. If you increase normal force, it increases friction. So this force technically doesn't do any work, but it adjusts another force that does do work. Does that make sense? All right? All right, what's number 3? C, right? This is positive work, but as I discussed in the video, we didn't get to it much yesterday, is all of that force doing work? No. Only the horizontal component is doing work, right? But in the case of D, right, where the force is all in the direction of that movement, all of that force is causing an increase in the energy, right? In the video, right, we discussed that work is equal to F times S, the force of the force that's being applied times the displacement of that object, or the distance, right? That's what the D is in this. Okay, D and S are the same thing. Yes. Right? But more accurately, we can adjust this formula to look like this, where we add in the cosine of theta. Theta is the angle between which way it's going and which way the force is being applied, right? This cosine theta term automatically isolates the horizontal component. And so this takes care of the fact that only horizontal components or only forces in the direction of motion do work, right? We can apply it to any situation, though. In case D, right? So green, right? In case D, no, that's not the one I wanted. That's the one I wanted. In case D, that was a lot just to circle that into green, but anyway. Force is going to the right, distance is going to the right. What is the angle between those two? It's actually 0. Force this way, if we think of like my two arms as an angle, right? Force this way, distance that way, right? That's 0 degrees. What's the cosine of 0? Anybody remember?
Oh, cosine of 0 at this side, pi.
Cosine of 0 is 1. Meaning, if we do force times 1, all of that force is going to being to cosine of 0 is 1. But on the other side, what's the angle between force and distance in case B?
180.
180. What's the cosine of 180?
0.
Negative 1. Negative 1, meaning that the work comes out as negative, right? But In the case of case A, right, the angle between force and distance is 90. What's cosine of 90? 0, and there is no work done in that case. Okay? So adding this cosine factor in here automatically isolates the component of the force that's doing the work. Okay? Good there? All right. Let's take a look at another practical application that relates to what we were just discussing and the relationship between work and energy. All right. So, okay. Work energy theorem shows us that the work is equal to the change in the kinetic energy. So this question, conceptual example 6.9, which I believe is on the back of the page that I gave you yesterday, it says, to accelerate a certain car from rest to the speed v requires the work w. Is the work required to accelerate the car from v to 2v equal to w, 2w, 3w, or 4w? All right? One of the reasons I like to give you a problem like this is because this is like standardized physics multiple choice question right here, right? A lot of times when you see multiple choice questions on a test like an ACT or an SAT or an AP exam or an IB exam, they don't give you numbers to work with, they just give you letters, and you have to look at the factors and the relationships between them, okay? All right, good there? So, first, what is this question asking us for? We have to identify that first, right? This question is asking us about what?
Is the work required?
Well, it's technically it's asking us about what? Is it asking us about kinetic energy? Indirectly. Technically, directly, it's asking us about what? Just start throwing out terms, Vlad. Just keep throwing out words. So, is the work, right? So this question is actually asking us about work, right? Now we know that work causes the energy of an object to change, specifically the kinetic energy of an object, right? So it's going to be beneficial to us to answer this question to examine the work, but we're probably going to have to look at the kinetic energy as well, okay? To look at the relationship between them. Also, we learned earlier in this section some other information they gave us in this problem, right? The kinetic energy of an object is determined by its what? What are the two factors that determine the kinetic energy of an object? Its mass and its velocity, right? So, probably a good idea to throw v in there as well, because that's going to affect the other two, right? So, it says, to accelerate a certain car from rest to speed v requires work w. So from rest to speed v. We have this picture here where we have the car in three different positions. It tells us initially what's the velocity of the car. 0. And then we can talk about if the velocity of the car is 0, what does the kinetic energy have to be? It has to be 0 as well. Okay. Now, because the kinetic energy is 0, does that mean the work is 0? No. In order to calculate the work, what do we have to look at? Say again? Final and initial. Work causes the energy to change. So we can't look at the work at any specific point. We have to look at the change from here to here. Okay? Does that make sense? So we can't really put work in this spot or this spot or this spot. We have to look at it from here to there. Okay? So it says that the car accelerates from rest to speed v. So in the second picture, right, That's there. And it tells us requires the work W. So going from here to here was work W. Okay? Does that make sense? Yes, no, maybe? It wants to know about this section right through here, right? That's what it's asking us for. And it says to go from this picture to this picture, what happens to the car? It's accelerating from V to 2V. So it's going twice as fast in this picture as it was in this picture. Good? Okay. That's all the information that they gave us in the problem. Now let's go through and let's kind of make some deductions, right, or make some connections. Although it doesn't give us a mass, we know that going from 0 to V requires an increase in the kinetic energy. They didn't really give us a mass, and they didn't really give us any numbers, but it's clear now that this car is moving and that it has kinetic energy. Yes? Okay. So I'm just going to fill in a generic KE in this spot right here. I don't know what it is exactly, but I know that it's KE. Right? Now, here's where we have to make some connections from earlier section of this unit. We talked about the relationship between speed and kinetic energy, yes? How are speed and kinetic energy related to each other? Not directly, not inverse. We got one choice left. Do we remember the formula for kinetic energy? It's quadratically, right? The kinetic energy of an object is equal to 1/2 mv squared, right? Meaning that if we double the speed, how much kinetic energy do we end up with? 4 times the amount of kinetic energy. That sound familiar from our discussion from Monday? All right. So that means that here, this car now doesn't have 2 KE, it actually has 4 KE. Yes, no, maybe. Good? Okay. Now, let's answer the question, right? What does the question mark in the picture now have to be? Well, kind of the same as the kinetic energy, but remember, work deals with what? Work isn't kinetic energy. What is the work? It's the change in kinetic energy, right? How much did the kinetic energy change in this section labeled the question mark in the picture? It only changed by 3. Yes? Does that make sense? It went from KE to 4 KE. That's a change of 3. Yes, no, maybe? Right? And that means that the amount of work done to go from V to 2V is equal to 3W. How's that? You okay with that idea? Okay. All right. That being said, let's examine what we saw in the video that I played for you at the beginning of class. All right. So here, I'll just draw it. So, okay. Here. What? Okay. How's that? Yeah, all of in my physics world drawing on the board, all cars are punch bugs. All right, so this car is driving along. Let's say it's driving along, I don't know, at some velocity v. Okay? It slams on its brakes, and this is not going to work. I know it, but I'll give it a try. Yeah, see, kind of. So let's go. It slams on its brakes, and eventually stops, right? So now its velocity is 0. Okay? It goes from having kinetic energy to no kinetic energy. Right? Meaning, if we use the same terminology as we did in the last problem, right? This would be work W. Yes? Good there? Okay. So, next picture, let me do this. Okay. Now, I'll move this card down here. I think most of us would realize that if this car is going twice as fast, it's going to take a longer distance for it to stop. Yes? In the video, they mentioned how much longer. Do you remember? It's not twice as far, it's quadruple or 4 times as much, right? Because now, going twice as fast, how much energy do you have? Not twice more, 4 times as much, right? And if you have 4 KE, now how much work do you have to do to get it to stop? Just that much. Because the work is the change is the energy, right? And this ends up with 0 energy, right? So it's that much, okay? Evan, go ahead.
So you go from 2 to 4 KE, you do that because you square
Exactly. Actually, yeah, you're squaring the velocity, but if we go twice as fast, that's 4 times as much energy. Yeah.
So no matter what the number is for velocity, you're squaring that.
Yep. Because of that equation, right? That whatever we plug into that equation, whatever we plug in for v, we have to square that number. Okay? Does that make sense? Now, let's do the distance, right? We said that work actually depends on 2 factors, right? What are the 2 factors that work depends on? What are the 2 things that contribute to the work done on an object? Force and displacement, right? What's the force that's stopping both of the cars in these 2 situations?
Oh, the tire and the ground.
What between the tire and the ground? Friction between the tire and the ground. The friction, oh, I lost Devin. He was answering a question before I was going to ask him a question again. That's okay. So let's see if we can pick up the slack for it.
How do cars
That's right. Austin's been out for like the last 20 minutes. So. It's okay. It's all right. Let him go. All right.
I have a question.
Hold on. Let me ask this question first. Okay. Let me ask my question first. All right. So, the amount of friction that's acting between the car and the road depends on the coefficient and the normal force. Yes? Regardless of whether this car is going a speed v or whether it's going a speed 2v, is the normal force any different?
No.
No. How fast you go doesn't affect the normal force. Is the coefficient any different? No. The force of friction in this example and in this example is exactly the same. Meaning that if we're going to have to do more work to stop the car, the only thing that we can do is increase the displacement. But not twice as much, 4 times as much. All right? Good there? Okay? Questions there? Now let's do the good. Technically slightly, but the air friction is negligible compared to like this, compared to the solid friction that acts between the tires. So, okay. Joe, go ahead. Yes. Okay. Now, let's talk about brakes for a second here. All right. Brakes work by friction.
No. You stop it, the wheel turns slower.
Yes.
But that's not friction. Friction is like stop the wheel completely and slide.
So, well, let's talk about friction in this case, right? There are 2 types of friction, right? There is dynamic friction and there is static friction. Okay? If I take this book and I slide it across the floor, right? That's what kind of friction?
Static.
No. That's dynamic or sliding friction because the 2 surfaces are moving. Right? However, good. No. Because the wheels actually work on static friction. Because if you think about how a wheel moves, right? As the wheel turns, only one portion of the wheel is in contact with the ground at any particular moment. Does that make sense? And they don't. That surface doesn't slide. It's just a new part of the tire continues to touch the road. Tires on cars and bikes too actually works on static friction, not dynamic friction. Okay? Now, Joe, going back to your original question. Are we familiar with the term anti-lock brakes? Okay. Yeah, when you slam on the brakes, you hear that like sound. What it's doing there is it's not letting your wheels totally lock up. If your wheels totally lock up and don't spin anymore, the friction turns from static friction into dynamic friction. Does that make sense? Like the book. But, hopefully remember from last unit, which coefficient is higher, static or dynamic?
Dynamic is
Static friction has a greater coefficient than dynamic friction. Remember, it's harder to get something to start moving than it is to keep it moving. Because you have to reach that peak. So by keeping your wheels turning, like your anti-lock brakes, it actually changes the friction from dynamic friction into static friction. And static friction is greater than dynamic friction. Well, that we're talking about, you're actually talking about going faster, but anti-lock brakes work on friction, but they just keep it more as static friction instead of dynamic friction, which causes the car to stop in a shorter distance. Because now, when we talk about work being done, right, we got to have force and we got to have displacement. If the force changes from dynamic friction to static friction, that's a higher force, that's less displacement that you have to use to stop the car. Does that make sense? Good there? All right. The formula that they showed you for the braking distance versus the coefficient of friction, that comes straight out of this formula right here. But I don't have time to show it to you right now because the bell's going to ring. So, is the bell going to ring? Yeah, bell's going to ring. So, I don't have time to show that to you right now. Maybe I'll show it to you tomorrow before we get into conservation. Hey, if you haven't done so, If you look at the calendar, there is homework on Monday night and there is homework on Tuesday night dealing with the relationship between energy and work. Answers are posted for both of those. I will make the homework tonight just the same homework from yesterday, the work application, so if you didn't do it, it's there. We'll push conservation back to tomorrow, okay?